Okay, so here is question 30 from the 2016 state math counts. So to start off, the most important thing to do first is to obviously draw a diagram. And so I'll do my best. It's quite hard to draw, even harder to draw on an iPad. All right, that'll do. And then we have this point here, and then a height. And so we have this triangular prism right here. This is our triangular prism. Oh, they don't actually concur. Probably go from here actually. So we have this kind of triangular prism with height 1, and the hexagon also has side length 1. And so we're given that our game die, it consists of 2 of these pyramids. So it'll be something like this, and then, okay, actually, yeah, that won't work. But anyways, we'll have then like another vertex over here. This is not the best diagram. Okay. But in essence, we have this like pyramid. It looks kind of like a cone. And then we have another cone on the other side. So I'm just going to draw with the cone. Cone. And we have another cone. Oh, another cone on this side. And then, so what we're asking for is how high off the ground is the opposite face? And so what this is really asking is what's the distance between, what's the distance between, like, for example, this face and the corresponding face over here? And so we know that the shortest distance is perpendicular to both. Since these 2 triangles are both parallel, clearly, I think this was stated earlier, that the angle to the base, to the angle to this plane is the same for both of them. So these 2 bases are parallel, and we're trying to find the distance between them. So that means that the distance will be the length of the perpendicular between them. And so that length will be this thing. It'll just be, and we can shift. Since these 2 lines are parallel, the distance between them is constant. So we can shift it, and we can take the line that's perpendicular to both of these faces through the center of our hexagon. And then this is actually just 2 times this length right here. And so now what we've really shown is that we're trying to find 2h. Our answer is 2h, where h is the distance from the center of the hexagon to one of the faces. And so now we can use one of the best tricks that you have in geometry, especially at the MathCounts and AMC level, which is calculating the volume of something in 2 ways. So now we're going to calculate the volume of this figure. Or I can redraw this as, so this is 1/6 of the hex. This is part of the hexagon. And then this is the height of 1. This is the height of 1. This is the part that's coming out of the pyramid. And then, so I'm going to label some points. So this is O, this is P, this is A, this is B. So this is point O, this is point A, this is point B, and this is point P. And so as I said earlier, we're trying to find H, where H is the distance from O to PAB. That's what we're trying to find. And so we actually know that this OABP is a triangular prism. So one way to find the area would be to say that's the area of triangle PAB times the distance from O to PAB, base times height, over 3. So that's one way to see it. That's one way to write the volume. But we can also find the volume another way, because we know this side length, we know this, and like we know a bunch of things. We can also say that the volume is equal to PO, height, times the area of triangle OAB, all over 3. But we know PO, it's 1. That's we're given that the height of the triangular prisms are 1. And then OAB is just an equilateral triangle with side length 1. So it is area √3/4. And so now we can set both sides to be equal to each other. I'm going to drag this down. A bit more space first. Okay. So we have these things are actually equal now. So we can write, for example, triangle PAB times the distance to O, the distance from O to PAB, which is H. So the area of triangle PAB times H equals √3/12. And both of these are equal to the volume. The volume is √3/12 of this OPAB thing. And now we can also find the area of triangle PAB. We know the length of PA. Let's draw out PAB. So here's PAB. We know that AB equals 1 because OAB is an equilateral triangle. PA is √2 because of the Pythagorean theorem. Same with PB. And so we can find the area of triangle PAB by dropping this perpendicular. This half length is 1/2, and then by the Pythagorean theorem, the height here, because of the Pythagorean theorem, this length is √7/2, because it's square root of 2 minus 1/4, which is 7/4. So the height is √7/2. So the area of triangle PAB is just √7/4. So √7/4 times H equals √3/12. That means that H equals √3/12 times 4/√7, which equals forgot about the over 3. Yeah. The volume on the left-hand side is base times height over 3 as well. So there should be a divided by 3 over here. So we get that √7/12 times H equals √3/12. And canceling canceling the over 12 from both sides, we get that H equals √3/√7. And so our answer is 2H equals 2√3/√7, which equals 2√21/7. So 2√21/7 is your answer. So the main idea here was to first figure out that the distance between the bases is just 2 times the distance from the center of the hexagon to one of the faces, because like the center of the hexagon is like at the center. It's obviously halfway between the 2 faces that we're trying to find the distance between. And then secondly, to find that distance from the center to a face, you can, that like figuratively screams for you to use the volume of an area formula, because you know the distance, if you know the distance from a point to if you know the distance from a point to like a triangle, then you know the volume of, then you can calculate the volume of that, of like the prism, of the triangular, of the pyramid defined by those 3 points at the base, and then that point you know the height from. And then if you can calculate the volume in a second way, which you often can, because these figures are like guaranteed to be rigid and like defined. So you can find the volume in a second way, and then you can solve for the height. Okay,